Okay, in this lesson, I want to get real with you all. And of course, I'm talking about real numbers. We're going to talk about briefly the different types of real numbers. First of all, before we talk about real numbers, know that there are real numbers and there are also what we call imaginary numbers. And imaginary numbers, you'll typically deal with them when you get to Algebra 2. They deal with the square root of -1. So with real numbers, we don't take square roots of negatives, but when we start dealing with the square root of -1, those are known as imaginary numbers. But for now, in Algebra 1, we're only going to deal with real numbers. And the good news is that there are only two types of real numbers. There are rational numbers, and there are irrational numbers. The word rational and irrational, the root of these words that's important to understand is the word here, ratio. Ratio. Okay? So the difference between a rational number and an irrational number is that a rational number can be written as the ratio of two integers, while an irrational number cannot be written as the ratio of two integers. All right? And that's basically it. So we further divide rational numbers into more categories. So the first category of rational numbers is known as integers. A subset of integers is known as whole numbers. And another subset of whole numbers is what are called natural numbers. All right? So we can give some examples of each of these. So starting with the natural numbers, these are our counting numbers. The natural numbers start at the smallest natural number is the number 1, and then it goes up by 1, 2, 3, 4, all the way to positive infinity. All right, these are the natural numbers. They're also known as the counting numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to infinity. Natural numbers do not include decimals. All right, the natural numbers are all they're all 1, 2, they're all non-decimal numbers. Whole numbers are very similar to natural numbers, or the natural numbers again are also known as counting numbers, except the whole numbers include 0. So whole numbers start at 0 and go to 1, 2, 3, 4, 5, all the way to positive infinity. All right? Those are our whole numbers. Integers are like the whole numbers, except for they are the whole numbers and their opposites. So the integers go to negative infinity, which if you can imagine an infinitely small number, that's negative infinity. So it goes from negative infinity. It includes all the negative numbers, but still we are not dealing with decimals. So these are numbers like, say, -3, -2, -1, 0, 1, 2, 3, 4, all the way to positive infinity. All right? So that's a terrible infinity. So these are our integers. So these are the negative and positive numbers, non-decimal numbers. You can also think of them as the whole numbers and their opposites. Okay? So the smallest whole number is 0. The largest is infinity. The smallest natural number is 1. The largest is infinity. The smallest integer is negative infinity. It includes all the negative non-decimal numbers all the way to the positive non-decimal numbers and infinity. Those are the integers. And then finally, we have rational numbers. So rational numbers are generally numbers, like we said, that you can create a ratio with these numbers. So these are our decimals and our fractions, because by definition, a fraction is the ratio of two integers. So I have a fraction such as 3/4. Okay, that is the ratio of the integer 3 and 4, or the whole numbers or the natural numbers 3 or 4. And I can convert rational numbers into decimals. So 3/4 I know is equal to 0.75. All right, so any decimal number, including the repeating numbers, are considered rational numbers. So a number like 0.111 repeating, for example, is a rational number because although it repeats indefinitely, I can make a fraction out of this. I can make this the ratio of two whole numbers. This is 1/9. Okay, if I do 1/9, that gives me 0.1 repeating. Same thing if I had a number like 4.5. All right, I can make a fraction out of this that is the ratio of two whole numbers. I know that 4.5 is 4.5, and I know that as a improper fraction, that is 9/2. So if I take the ratio of the integers 9 and 2, that gives me 4.5. So any of my decimals, even in my repeating decimals, these are all considered to be rational numbers. All right, so don't be thrown off by repeating decimals. So again, even if I had a decimal like 0.12, 12, a repeating decimal such as this is a rational number because I can create a fraction to represent this. This is 12/99. That's not in simplest form, but this will give you that fraction. So therefore, this is a rational number. So generally speaking, our decimals are all of our terminating decimals. So a number like 0.75 is called terminating, means it stops. The decimal ends. That's a rational number. Our repeating decimals, okay, these are also rational numbers. So all of these are the types of rational numbers that we have. Irrational numbers, as the name suggests, irrational means that you cannot create these numbers based on the ratio of two integers. All right. So irrational numbers, these are what we call our non-repeating. And non-repeating means there's no pattern in the repetition. All right. So there's no pattern. And non-terminating means it doesn't end. The decimal does not stop. Okay, doesn't end. The decimal doesn't end. So these are non-repeating, non-terminating decimals. That is the definition of irrational numbers. Irrational numbers are non-repeating, non-terminating decimals. Many of the irrational numbers that we can give examples of are given special symbols in mathematics. So for example, there is a number that we call the transcendental E. All right, the transcendental E is just, we represent it in mathematics as the letter E, but it represents an irrational number. That's why we use a variable, lowercase e, to represent it. So the transcendental E, if you have a scientific calculator, you can probably find this key on your calculator, and we can approximate it as 2.718, 281828, and so forth. All right, this is a non-repeating decimal in that it has no pattern. All right, it has no repeating pattern, and it has no end. It doesn't terminate. So if you look here, there is no pattern. It's not 718181818. No, it doesn't repeat. So 7182818828, and it just goes on forever. So your calculator will typically estimate this number to, let's see, this one did, 6, 7, 8 or so digits. But ultimately, we know that the number continues forever. So this is an irrational number. So anytime you see the transcendental E, that is an irrational number. In geometry, if you take the ratio of a circle's circumference to its diameter, it is typically in mathematics courses represented by the Greek letter pi. But in my classes in African mathematics, we say that since the Greek alphabet was not invented until thousands of years after this particular geometric constant was in use in engineering and architecture in the ancient African Nile Valley, we said it doesn't make sense to use a Greek letter to represent something that was not founded by the Greeks. So we use the letter from the Medo-Neter alphabet known as Wa, which looks something like this. And this represents the constant that is a circle's circumference to its diameter, but which you probably are familiar with as pi, but in this class, in my classes, we call it y. Y is an irrational number. It is a non-repeating, non-terminating decimal. So we can approximate it as 3.141592654, and so on. The ellipses here, the three dots, means that it is non-terminating, means that it does not end. So the decimals continue to go. Our calculators just approximated, let's see, 3, 6, 9. Our calculators approximated to 7 decimal points, but it continues forever. So we add the ellipses, the three dots, to represent it as non-terminating. It is also non-repeating, meaning there is no pattern. So if you look at the decimal point, there is no pattern in the numbers here. All right, it's not like 0.121212 where there's an obvious pattern. It's just 1 and 2 repeating, or 0.111 repeating where it's an obvious pattern. There is no pattern. Okay, another example of irrational number are square roots of non-perfect squares. So for example, if I have the square root of 2, all right, 2 is not a perfect square. So therefore, if I take the square root of 2, it is an irrational number. It is a non-repeating, non-terminating decimal. So if we use our calculators, we can approximate it as 1.4142135562 and so forth, but it does not end, it is non-terminating, and there is no pattern, so therefore it is non-repeating. So any non-perfect square, so numbers like the square root of 2, the square root of 3, the square root of 4 is a perfect square. So the square root of 4 is 2. So the square root of 4 is not an irrational number. But the square root of 3 is an irrational number. The square root of 3 is approximately 1.732050808 and so on. All right. So all of these are irrational numbers. So the key here is that irrational numbers, they're probably represented in a funny way. So they're either given some kind of variable such as e, or in my classes we use y instead of pi, or they're in the context of a square root. That's typically how you can identify an irrational number. But the key is what makes it irrational. It's non-terminating, it doesn't end, and it's a non-repeating, or i.e. a no-patterned decimal. If you have a decimal that has a pattern, 0.121212 or 0.456456456456, that's a rational number. You can create a ratio of two integers. You can create a fraction to represent that decimal. Right? These are rational numbers. If the rational numbers are non-decimal numbers, and it includes the negative non-decimal numbers, those are integers. If they are only the positive non-decimal numbers and 0, those are whole numbers. If they are the counting numbers starting from 1 with the other non-decimal numbers going to infinity, those are the natural numbers. These are our sets of real numbers. All right. So be able to recognize these numbers. But ultimately, even though it's important that you know to recognize them, we're going to be doing the same thing. So regardless of whether you're dealing with a natural number, an integer, or an irrational number, all of the operations stay the same. All right. That's it. That's how you do it.